I'm going to present Semantics-Controlled Gaussian Splatting for auto scene reconstruction and rendering in virtual reality today. So last year I was in New Zealand and I sent a lot of pictures to my family and friends. And of course, they enjoyed looking at the pictures, but they were never really locally in New Zealand and also could not travel there. So I wondered if there's a possible way that people who cannot physically travel or do not want to travel due to environmental issues, how could they experience worlds far away from their local place? So one way is virtual tourism. A very easy way to do that is to create a panoramic image or video from a place, maybe add some depth estimation, and then people can actually see the photo or video in VR. Another option is a 3D reconstruction, because with that people can actually move freely in the space and are not restricted to the camera position where the scene was recorded. One way to do this is Gaussian splatting, which derives from classic rasterization, where the Gaussians are optimized in a 3D space and you basically have an optimized point cloud. The classic Gaussian splatting is a static reconstruction of an environment that you can see here, highlighted with the word static reconstruction. And one thing, which is the problem of static reconstructions, places like water or the sky, there are no moving clouds, there's no moving water. So the question is, how could we achieve this? And this is actually what our solution provides. We can replace parts of the environment with some dynamic 3D assets, which are available within game engines anyways. And with our approach, you can remove parts of the scene to be replaceable with such 3D assets. If we talk about the technical perspective, what do we achieve, or what is one of the problems that we solve? So classic reconstruction for novel view synthesis like Gaussian splatting, there you normally circle around an object and then you have a very beautiful reconstruction of that part of the scene. But our problem statement and what we tackle more is the camera trajectory you can see on the right side. So we have a continuous forward motion, which is a little bit untypical from classic novel view synthesis approaches. And something else that we have, which is a problem for the separation of the 3D Gaussians, is our images are a little bit more complex in terms of similarity and feature similarity. So you can see here a lot of reflections, for example, on the right image. This is an image from our dataset, and our dataset is also part of the contribution from our paper. On the left side, you can see an image which is normally used to evaluate Gaussian splatting and semantics, which has a way lower feature similarity compared to our right image. One approach which solves Gaussian splatting and editing of scenes is Gaussian grouping, which is normally evaluated on such images like on the image from the left side. And what it basically does, it extends the normal Gaussian splatting rasterization process and adds the learning of a feature field, which is then separated, or the classes are assigned with a classic classifier from deep learning. And our approach solves all of this a little bit differently. So approaches like Gaussian grouping, they actually use segment anything to get their segmentation ground truth. What we do, because we will also later see this, segment anything does not work super perfectly and smooth on our auto data. What we do is we use some pre-trained supervised network to get the segmentation ground truth of our outdoor data. You can see that here. We use CallMap to get the camera poses, and then we use the classic rasterization process to get the RGB part of the Gaussian splatting. And what we do differently from existing work is that our rasterization process directly assigns one ID per Gaussian. So when we later want to edit the scene, we do not need any classifier or so which separates the feature space. Instead, each of our Gaussians gets a direct assignment in the 3D space, which allows easier editing of this forward motion that we have in our dataset. And with our approach, what we can do, we can, for example, remove the sky like here, and then add it to our game engine, add some virtual assets like the water or the kayak, and then a person can move freely in our Gaussian splatting created world. We, of course, also evaluated our approach. So we evaluated it from a technical perspective, evaluating PSNR, SSIM. More details can be found in the paper. We compared with Gaussian grouping because it's the most related work to ours. For Gaussian grouping, as I said, they normally use segment anything for generating the segmentation ground truth, but this actually introduces a lot of problems with our outdoor data, why we use these supervised labels I showed before. And we also, for fair comparison, of course, use these supervised labels also for Gaussian grouping. You can see that different labels highly impact the novel view synthesis results. But with our approach with direct rasterization process, we actually got a better PSNR value. For SSIM, we are on par with Gaussian grouping. If we use our labels, if we use the official Gaussian grouping approach, we are actually better than the state of the art. If we look at the segmentation, so on the left side, you can see Gaussian grouping with our labels. On the right side, you can see our approach. If we look at the rendering, they look almost the same. You can see here some outliers. If we look at the segmentation, this outlier is also present in the segmentation, which is also visible here. So as I said, Gaussian grouping has a feature space which they separate, and we have this direct assigned IDs, which they basically show clearer object boundaries, which is highly beneficial for such outdoor scenes like we propose in our dataset. If we come to the main task, because what we want to achieve is that we want to replace parts of the scene with some more appealing parts from the game engines and also allow more interactability with the environment. What we can see here, the feature space is not super clear at some 3D features, which probably makes it also difficult to remove parts of the scene. We can also see that here. And also Gaussian grouping initially uses a convex hull to remove parts of the scene, which is not super beneficial in such a forward motion, which is why we apply a direct removal. We can see what happens to Gaussian grouping if we do direct removal. There are still some outliers and some parts of the scene are removed. And from some parts of the scene, there are too much Gaussians removed. If we look at our approach, we can also see that at the borders, there could be some jittering potentially generated segmentation masks, but actually we have way clearer boundaries compared to Gaussian grouping. And we can, for example, especially see it here in the sky or here on the tree and also here in the whole environment. So if we come to the point where we have all this technical stuff working, the next logical step is, of course, to also evaluate it. So how would a user perceive this whole environment? So what we did is we run a pilot study first where people were tied to the camera path and had the option between the panoramic video and also classic Gaussian splatting, and our approach where we replaced parts of the scene. And we had our main study where we then gave the user the freedom to move, so that what we want to initially achieve, that people who are not traveling somewhere can actually move freely around in the surrounding. And we selected some spots where we also asked the individuals some questions about the current environment they're perceiving. In our pilot study, we had 24 participants, and in our main study, we had 30 participants with no overlap to the pilot study. From our pilot study, we basically found that if we follow the original camera path, people prefer the panoramic video the most because it was the most realistic one. If we look in our main study, we actually found that with our approach, people found it more visually coherent, for example, in terms of reflections. And in general, we had a higher sense of presence for our approach when compared to traditional Gaussian splatting. So in summary, we have a novel 3D asset generation approach. We have a new challenging outdoor data set. We have a user study on presence and quality of our approach. We can show technical superiority in scene editing when comparing with the state of the art. And in general, we have broad applicability, even with more use cases in our paper. Thank you for your attention. You can also already download the dataset, and it's available at Open Science Foundation.